Good morning and welcome to this the lecture number 23 of the course Stochastic Hydrology. In the last lecture we introduced the concept of Markov chains. If you recall, we said Markov chains are the stochastic processes where we can write probability of x t given the entire history of the process x t minus 1, x t minus 2 etcetera up to x 0 as equal to probability of x t given x t minus 1, which means the memory of the process is limited to only what has happened in the last time step. These kind of Markov chains we use when we are analyzing, let us say, the drought runs and the flow sequences and especially the weather conditions. What is the probability that tomorrow will be a rainy day given that today is a rainy day, and what is the probability that next year will be a drought year when this year is not a drought year, and questions like that. So, Markov chains are very useful and powerful techniques. Markov chains is a good technique to analyze several of hydrologic problems. We also introduced the concept of transition probabilities, where we are talking about the probability of the process transiting from a given state in time period t to time period t plus 1 to another state in time period t plus 1. For example, we may be saying that what is the probability that starting with a dry day today, the process goes to a dry day tomorrow, or starting with a dry day today, state being in dry day today, the process goes to a wet day tomorrow. So, these kind of probabilities which relate the transition from a given state in a particular time period to a given state in the next time period. These probabilities are called as the transition probabilities. And starting with the transition probabilities, we introduce the concept of the probability vector. What do we mean by probability vector at a particular time step n? It consists of the probabilities of going into certain states in that particular time step. We wrote p to the power n or p of n as the probability vector at time step n, and the vector consists of elements p j n, that is the probability of going into state j in time step n. From that we developed the concept of steady state probabilities, or they are also called as limiting probabilities. As the process goes far into the farther into time, then the probability vectors converge to the steady state probabilities, in which case we wrote, if you recall, small p is equal to small p into capital P. Capital P is the transition probabilities, small p is the probability vector. The determination of steady state probabilities is important when we are looking at the Markov chains. The steady state probabilities will indicate for a given process what is the probability that it goes into state j when the process has reached steady state. For example, you are looking at reservoir levels. So, you may be interested in the steady state probability that the reservoir level will be between 50% and 75%. Or if you are looking at the drought lengths. So, you may be interested in what is the probability that a given year will be in drought situation. So, these are the steady state probabilities. So, given the transitional probabilities, we must be in a position to determine the steady state probabilities. So, what we will do in today's class is, starting with those definitions that we introduced in the last lecture, we will solve some examples to make sure that we understand the concepts that we have introduced in the last lecture. So, let me begin with the summary of the last lecture again. We have introduced the concept of the transition probability matrix and the steady state Markov chains or the steady state probabilities. So, if you recall, we wrote the Markov chain as probability of x t given x t minus 1, x t minus 2 etcetera x 0 as equal to probability of x t given x t minus 1. We also called this as the one step Markov chain or single step Markov chain, and typically we write the states as probability that x t is equal to a j, that is it indicates that in time period t the process has gone to state a j, given that in time period t minus 1 it was in state a I, and this probability we indicate it as p I j t. This indicates the probability of transiting from the state I in period t minus 1 to state j in period t. So, if you are taking two time periods, two adjacent time periods, it was in state I in period t minus 1 and it goes to a state j in period t minus period t with a transition probability p I j t. Relate this with, let us say t minus 1 was in the state dry state, which means there was no rain. There are two states, for example, no rain and rain or dry and wet. So, it was in no rain condition. What is the probability that it goes to a no rain condition, or what is the probability that starting with the no rain condition in time period t minus 1, it goes to a rain condition or wet condition in period t. So, these transitions are governed by the transition probabilities denoted as p I j t. So, this is the transition probabilities. Then we defined the n step probability vector as equal to p 0 into p to the power n, where capital P is the transition probability. So, p to the power n, p 0 is the probability vector at time 0. So, given p 0, we must be able to get the probability vector at any given time step n. Now, as n increases, the dependence of p to the power n on p 0 decreases, and in fact, p to the p n, that is the probability vector at time step n, converges to a certain steady state values, and at that time we call we say that the Markov chain has reached the steady state, and then we reckon the probabilities at that state as steady state probabilities. Steady state probabilities will be given by p is equal to p into capital P. So, the solution of this will give you p, but typically as I said in the last lecture, you keep on getting p of n with increasing n. Let us say you get p 2, then p 4, p 16, like this you keep on getting p 32 and so on, p 16 into 6, p 16 to the power 2. As n keeps on increasing, you will see that the p to the p of n will converge to certain steady state values. So, instead of using this, you can use this and keep on increasing n until you obtain a probability vector which converges, and that is when you can call those probabilities as steady state probabilities. You can also use this to verify that. We will do that through a numerical example. So, let us now get used to the concept of the transition probabilities. So, essentially what we do in the transition probabilities is we assign probabilities for the transition from one step to another step. Say for example, we are talking about, let us get used to this concept first, that we are saying that there are two stages or two steps, I am sorry, two states 1 and 2. Let us say this is state 1 and state 2. This refers to the time period t or time period t minus 1. Let us say we are talking about the transition from period t minus 1 to period t. So, this states are for period t minus 1 and these states are for period t. You will have again states 1 and 2. Let us say you are talking about the day being a dry day or a wet day. I may say the process is the weather process is in state 1 if it is a dry day, it is in state 2 if it is a wet day. Then the probability that from a dry day it goes to dry day, that is, given that today is a dry day, what is the probability that tomorrow is a dry day? We may say this is 0.7. That means, it is the probability that it goes from a dry day today to a dry day tomorrow is 0.7. Then this has to be 0.3. Remember, the transition probability matrices are stochastic matrices where all the rows add up to 1. So, the probability that it goes from state 1 to state 2 will be 1 minus of this if you have because you have only 2 states. So, this will be 0.3. Let us say you are already in state 2, that is it is a wet day. What is the probability that from wet day you go to a dry day? So, 2 to 1, that transition, let us say it was 0.4. So, this was 0.4, then this will be 0.6, that is from state 2 to state 2. You must always keep in mind that we are talking about 2 adjacent time periods t minus 1 to t, and this is the transition probability that we are talking about from 1 to 2 or 2 to 2, 2 to 1, etc. So, you will have 4 such probabilities in this case. Now, another important aspect that we must remember is when we formulated the TPM, that is the transition probability matrix, we had m by m probabilities. Let us say I write P is equal to, if you recall, P 1 1, P 1 2, etc., P 1 m. You have m steps, m states, and P 2 1, P 2 2, etc., P 2 m, and so on. So, you have P m 1, P m 2, etc., P m m. So, the transition probability matrix is a m by m matrix, where m is the number of states, and this you can write this as t minus 1, 1, 2, 3, etc., m. So, in time period t minus 1, it occupies the state 1, 2, 3, etc., up to m. Then these probabilities give the probabilities of the transition from a given state in t minus 1 to a given state in period t. This is a general notation. So, it is a m by m matrix where m is the number of states. From the data, we know how to determine these transition probabilities. Yesterday in the last lecture I explained that from the data you should be able to arrive at each of these transition probabilities. How many such values you need to estimate? There are m square values, but the last value in any of the rows can be obtained by using the remaining m minus 1 values. So, you will have m into m minus 1 number of values that you need to estimate from the data. So, given the historical data, you discretize that. Let us say you are talking about the stream flows at a particular location, you identify the states that you are interested in, depending on, let us say when I call it as a state number 1 when the flow is between 0 to 100. I call it as state number 2 when it is between 100 and 200, etc. Like this, you identify the states first, states of the Markov chain, and then you look at the historical data, assign states corresponding to the actual flow values that you have obtained, and then look at the transitions from one time period to another time period, how the transition has taken place, from starting with the state number 1 in let us say month of June. Where did it go? Did it go to class number 1, class number 2, how many times did it go to class number 1, etc. Like this, on the relative frequency approach, you will obtain the transitions, the transition probabilities P11, P12, etc. So, from the historical data you would have estimated the transitional probabilities. The transitional probabilities are the single most important requirements for analyzing the Markov chains, single step Markov chains. So, let us do a simple example now. We will look at the weather conditions, the dry and wet weather conditions, and see how we analyze that. Let us say we have two states, and the state 1 is a non-rainy day and state 2 is a rainy day. We also can call it as a dry day and a wet day. Now, we will obtain first the probability that day 1 is a non-rainy day, given that day 0 is a rainy day, and the transition probability matrix is given here. So, this is state 1, state 2, and this is state 1, state 2. So, starting with state 1 in any day, the probability that it goes to state 1 the next day is 0.7. Starting with state 1 in any day, the probability that it goes to state 2 in the next day is 0.3, like that. So, we are given that day 0 is a rainy day. So, this is non rainy, this is rainy. So, we know that day 0 is a non-rainy is a rainy day. So, you are looking at this state now. So, you are in state 2 in day 0. Then what is the probability that day 1 is a non-rainy day? So, going from a rainy day to a non-rainy day, this is 0.4 itself. So, directly from the transition probability, you know that the probability of going to a non-rainy day is 0.4 here. So, that is what is written here, probability that day 1 is a non-rainy day, given that day 0 is a rainy day. So, you have no rain, rain, no rain, rain, these are the two states. So, from a rainy day you want to go to a non-rainy day. So, the probability is 0.4. Similarly, from a rainy day, if you want to go to a rainy day, the probability is 0.6. So, this is the interpretation of the transition probabilities. Now, we will look at the second problem, which is second sub problem, so to say, probability that day 2 is a rainy day, given that day 0 is a non-rainy day. So, you are starting with a non-rainy day, you are given that you are in a non-rainy day. What is the probability that day 2, not the next day, but day 2 is a non-rainy day, I am sorry, day 2 is a rainy day. For this, what is it that we need to do? We must get the probability vector of day number 2. So, day 0 is given and you need to get probability vector of day 2. What does the probability vector give? The probability vector at a particular time step gives the probability of being in a given state in that time step. So, P of n, I repeat, P of n is equal to it gives P j of n, it is a row vector consisting of P j of n, which indicates that in the time step n the probability of being in state j is given by P j of n. So, for any time step we need to determine the probability vectors for that particular time step to determine the probability that the process occupies a particular state in that time. So, in this particular problem what do? We obtain the probability vector for day number 2, given that day number 0 is a non-rainy day. Because you are given that day 0 is a non-rainy day, you are looking at this vector 0.7 and 0.3. So, P 1 in this case is directly 0.7 and 0.3, because you are given that you are in non-rainy day. So, what is the probability that in day 1 you go to a non-rainy day? It is 0.7. What is the probability that you go to a rainy day in day number 1? It is 0.3. So, P 1 in this case is 0.7, 0.3 itself, because it is given that day 0 is a non-rainy day. And P 2 we write it as P 1 into P. Recall that we wrote p to the power n is equal to p of n is equal to p of n minus 1 into p. So, p 1 is 0.7, 0.3 because we are looking at, we are given that day 0 was non rainy day, then we know the probabilities of going into a non rainy or rainy day on day number 1, and therefore, p 1 is given. So, we will go to p 2, p 2 is calculated as p 1 into p, where p is the transition probabilities. So, we calculate p 2 as 0.7, 0.3 and the transition probability, which is 0.61 and 0.39. What does this mean? This is no rain and rain. So, this is no rain and rain, and we are interested in getting the probability that day 2 will be a rainy day. So, day 2 is a rainy day is what we are interested in. So, day 2 is a rainy day is 0.39, day 2 is a non rainy day is 0.61. So, this is a probability vector, and therefore, the required probability is 0.39. Then we will look at the third sub problem, which is probability that day 100 is a rainy day. That means, far into the future. We are given that day 0 is a non rainy day, we want to get the probability that day 100 is a non rainy day. I am sorry, day 100 is a rainy day. Either way, once you get the probability vector for any particular day, you will be able to tell what is the probability that it is a non rainy day, or also what is the probability that it is a rainy day. So, recall that we wrote p of n is equal to p of 0 into p to the power n, that is starting with the probability of probability vector of time step 0. We write this to obtain the vector probability vector for time step n. So, we need p to the power n. Actually, what we are doing now is, you can write p 1 first, then from p 1 you obtain p 2, from p 2 you obtain p 3, etcetera. Like this, p of n is equal to p to the power 0 into p to the power n. So, as you progress well into the as a Markov chain process progresses well into the time, then the p to the power n, p of n converges to steady state probabilities, and therefore, p to the power n is what will be governing the steady state probabilities. So, let us look at p to the power n. So, p square, this is the transition probability, p square is equal to p into p, which is this p into p, you get 0.61, 0.39, 0.52, 0.48 when you multiply p into p. Then p to the power 4, which means we are obtaining the probability vector at time step 4, at day number 4. Then p 4 will be 0.7, that is p square, whatever we obtained, you multiply it again by p square. So, you get this vector, this matrix, I am sorry. Then p to the power 8, which is p to the power 4 into p to the power 4. So, 0.5715, 0.4285, etcetera, like this. Then we will take p to the power 16, which is p to the power 8 into p to the power 8, that is 0.5714, 0.4286, 0.5714, 0.4286. What is happening here? These values are slowly converging. Not only that the individual values are converging, but the column, each of the columns converges to a particular value, 0.5714 in this case, and here 0.4286 in this case. What does this mean? This means that the probability of non rainy day, here look at p 16, probability of non rainy day is 0.5714, 0.5714 irrespective of what was the starting point here. Similarly, the probability of rainy day is 0.4286 irrespective of what was the starting point, and therefore, this reaches a steady state, and in fact, the probability vector at any given time step will then be 0.5714, 0.4286. So, the probabilities have converged to these values, and therefore, we write the steady state probability as p is equal to 0.5714 and 0.4286. Let me just check what we said, this is a non rainy day and this is a rainy day. So, this is the probability of non-rainy day and this is the probability of rainy day. This means that for this particular particular example, we can say that the probability of the 100th day or day number 100 being a non-rainy day is 0.5714 and the probability of day number 100 being a rainy day is 0.4286. We had the condition for the steady state as P is equal to P into capital P. Now, this is what we obtained by simply raising the powers of capital P, which is a transition probability, and that is how we obtained this. Let us try to verify whether the P that we have obtained in fact satisfies this condition. So, P is equal to P into capital P. So, this 0.5714 into 0.4286 into the transition probability 0.7, 0.3, 0.4, 0.6. So, 0.5714 into 0.7 plus 0.4286 into 0.4, that gives you 0.5714 itself. Then 0.5714 into 0.3 plus 0.4286 into 0.6, that gives you 0.4286 itself. So, this is the steady state probability vector. So, this is how we obtain the steady state probabilities. As I mentioned, you could have straight away used this and then obtain the steady state probabilities, but in certain higher dimensions this becomes slightly cumbersome. So, the easier way of doing it is simply keep on obtaining the powers of the transition probabilities and see that the transition probability matrix when it is raised to higher powers, it converges to certain values, both the columns converge to certain values, and then you say that the steady state probabilities are achieved. But then you should verify that this condition is in fact satisfied by the steady state probabilities that you have so obtained. Let us look at another example now, where we will use the transition probabilities to generate the data. What did we do in earlier cases? We used ARMA models to generate the data. We used the Markov process, the Thomas Fearing model to generate data. We also used in our earlier examples, we used the probability distributions. When the process is uncorrelated, you use probability distributions to generate data. For example, we have studied how to generate data belonging to gamma distribution, how to generate data belonging to exponential distribution, and so on. Now, let us say that we have fit the Markov chain. What do I mean by fitting the Markov chain? That we assume that the process follows Markov chain and then we have obtained the transition probabilities. So, you have discretized or you have identified the states to which the process goes into in every time period t, time period t plus 1, time period t plus 2, etc. So, you have for every time period you have identified the states to which the process goes in, and then you have determined the transition probabilities using the historical data or otherwise. Now, we need to determine or we need to generate the states to which the process is likely to go into the future. Let us say that you had two states, one being a dry state and two being a wet state. Then can we generate a sequence much the same way as we generated a sequence of flows, or much the same way as we generated a sequence of data belonging to certain distributions and so on. Given the Markov chain, can we generate a sequence of states that the process is likely to go in? For example, next 10 periods, I want to say that it goes into state 1, it goes into state 2, etc., not with the probabilities, but now we will say that it is going into state 1, going into state 2, and so on. So, starting with the transition probability matrix for a given Markov chain, we now simulate or we now generate the states that the process is going into in future. So, that is the exercise we will do. So, for the data generation from a Markov chain, what we need the initial state, that means the starting state, whether it was a dry state or a wet state in that example, and then the transitional probability matrix. As I said, the TPM is both referred to as transition matrix, transition probability matrix, as well as transitional probability matrix. So, TPM. Then the initial state is known. Let us say that the time period t is equal to 1, the state is known. Then we want to determine the state at time 2. That means, we want to generate the state at time 2. What do? We get a random number R u between 0 and 1. You recall that any CDFs that we talked about, the cumulative probability distribution functions, cumulative distribution functions, if you take numbers randomly from a CDF, they follow uniformly distributed random number, uniform distribution with 0 between 0 and 1. So, we generate a RU. How do we generate RU? As I mentioned in the last class, you have a calculator, and most of the calculators will have random numbers. This we have done in the case where we studied the Thomas Fairing model. Let us say I pick up a random number. This is, it comes to be 0.767. The next number will come to 0.650 and so on. So, you can use the calculators. Most of the scientific calculators will have random number generators, and these random numbers are uniformly distributed random numbers between 0 and 1. So, we generate the random numbers and then look at the random numbers, compare it with the cumulative transition probability matrix. What do I mean by cumulative transition probability matrix? The number that you generate, which is between 0 and 1, if this RU is between the summation p I j up to n minus 1, where n is a state. So, n minus 1, and if this lies between the cumulative transition probabilities up to n minus 1 and n, cumulative probabilities up to n, then we assign the class interval n for that. So, this is how we generate. Now, let us say that the first class interval you generated as 2, then this becomes the initial class for the next value. Again you generate a random number, then look at for the next state, for the associated state, where does it belong, in which interval of the cumulative transition probabilities it belongs, then assign that particular class interval and so on. So, like this you are now generating the states of the Markov chain and not the exact values, as we did in our transition as we did in our earlier data generation problems. So, we are now generating the states of the Markov chain that will occur in future. So, let us do an example for that. You consider the Markov chain of annual stream flow at a location. Let us say we have 3 states for the annual stream flows. We say it is a state, it is in state 1 when there is a deficit flow. We may assign that as soon as the flow falls below a particular threshold, we call it as a deficit flow. So, that is state 1. Then state 3, we say it is a excess flow, flow above a particular threshold, we call it as excess flow, and then we also define state 2 as intermediate flow. Then we have the transition probability. So, state 1, state 2, state 3 here, then state 1, state 2, state 3 here. These are annual flows. So, given that this year is a deficit year in terms of the flow, what is the probability that the next year will also be a deficit year? Given that this year is a deficit year, what is the probability that next year the flows will be intermediate? Given that this is a deficit year, what is the probability that next year will be a excess flow? So, these are the probabilities. So, this is how we formulate the transition probability matrix. So, there are 3 states here, time period t minus 1 to time period t. So, these give the transition probabilities of going from deficit to intermediate, deficit to excess flow and so on. So, this last row here starts with excess flow, excess to deficit, excess to intermediate and excess to excess. So, that is how you get the transition probabilities. Now, given that these are the transition probabilities, we want to generate a sequence of states. For example, next 10 years we want to say that it is a deficit year, it is a intermediate flow year, it is a excess flow year, etcetera. Like this we want to generate for the next 10 years, let us say. How do we do this? First we construct the cumulative transition probability matrix. What do I mean by cumulative? You keep on adding across the rows. So, this will be 0.7, 1.0 and 1.0. Then 0.7, this is 0.1, 0.7, 1.0, 0.5, 0.9, that is I am adding these two numbers 0.5, 0.9 and 1.0. 1.0 will be the maximum number. So, you get the cumulative transition probabilities as 0.7, 1 and 1. Once you reach 1, you retain it as 1. Then 0.1, 0.7, 1, 0.5, 0.9 and 1. So, these are the cumulative transition probabilities. So, this is state 1, state 2, state 3. Any uniformly distributed random number that you pick, if it is less than 0.7 when you were in state 1, let us say you start with t is equal to 1 and you are in state 1 and you generate a uniformly distributed random number. If the uniformly distributed random number that you get is less than 0.7 or less than or equal to 0.7, you assign class interval 1 to that. If it is between 0.7 and 1, assign class 2 to that and so on. So, class 3 does not appear in this particular case. So, if you were in class 2 and you obtain a uniformly distributed random number which is less than or equal to 0.1, assign class interval 1. The uniformly distributed class random number is between 0.1 and 0.7, assign class interval 2. If it is between 0.7 and 1, assign class interval 3. This is how you keep on assigning the class intervals, and the class interval that you so assign for the next time period becomes the initial class interval for the next time period. And this is how you use the cumulative transition probability matrix along with the uniformly distributed random numbers to generate a sequence of states into which the Markov chain is going. So, this is what we will do. Let us say at time 1 we assume this is a starting state that is assumed or given. Let us say this is given state. Then you generate a uniformly distributed random number from the calculator. So, this is from the calculator or otherwise, if you are using a MATLAB program you can generate, if you are using Excel you can generate uniformly distributed random numbers. Most of the scientific programs, most of them have random number generators which provide you uniformly distributed random numbers in the interval 0 and 1. So, you get 0.896. So, look at this. You have the cumulative probability transition probability matrix, you are in state 1 and you are generating for state 2, that is for period 2, you were here. So, you got a number of 0.896 and 0.896 falls in this interval, that is between class 1 and class 2, you assign class 2 to that. So, that is how you get class 2 in the next time period. This class 2 becomes your starting point for time period 2. So, starting with time period 2 you want to generate for time period 3. So, in the time period 2 you got the class interval 2 and you generate another random number. This comes to be 0.919. So, you were here, you are in class interval 2 and 0.919. So, you are here between 0.7 and 1. Therefore, you assign class interval 3. So, that is how you go to class interval 3 or state 3, and that state 3 becomes your initial point for period 3, using which you want to generate for period 4. Again you generate another random number, it is 0.682. So, you are in class interval 3. So, you are here 0.682 falls in this region and therefore, you assign class interval 2, and that is how you get the state 2 here, and like that you continue. So, you generate 10 values like this and you can in fact generate a large number of values, much the same way as we did for your ARMA models or Markov model, Thomas Fearing model, or data generation using using the probability distributions and so on. So, this is how we generate states of the Markov chain. The Markov chain that we have been discussing are all one time step Markov chain, which means that we are writing probability of x t given x t minus 1 etcetera is equal to probability of x t given x t minus 1, which means the memory of the process is limited to what has happened during the last time period. There may be situations where the state at a particular time depends not only on the previous one, but also on previous 2 or previous 3 time periods. It is often advantageous to convert such multi-step Markov chains into single step Markov chain. For example, if we are given that the weather today depends not only on weather yesterday, but also on weather day before yesterday. That means, on the past 2 days weather, the weather today is dependent. In which case, we must be able to define the states properly in appropriate manner, so that we can treat this also as a single step Markov chain. Let us look at an example where the weather today depends on weather during the last 2 days, and then how we convert that into a single step Markov chain. So, consider that last 2 days weather conditions influence the today's weather condition. That is, whether or not today is a dry day or a wet day depends on the previous 2 days weather conditions, not just the previous days. In addition, if the past 2 days have been wet days, then it will be a wet day tomorrow with a probability of 0.8. So, yesterday and day before both were wet days. By wet day I may mean it is a rainy day, and the probability that today will also be a rainy day or today will also be a wet day is 0.8. If today is a wet day, but yesterday was we are using today and yesterday. So, let me put it this way: if today and yesterday were both rainy days or both wet days, then it will be a wet day tomorrow with a probability of 0.8. Then if today is a wet day, but yesterday was a dry day, then it will be a wet day tomorrow with a probability of 0.5. If yesterday was a wet day, but today is a dry day, then tomorrow will be a wet day with a probability of 0.3. Then if the last 2 days both have been dry days, then tomorrow will be a wet day with a probability of 0.1. Remember, we are talking about tomorrow being a wet day, all these probabilities are for tomorrow being a wet day. All right. Now, how do we convert this into a single step Markov chain? Let us say if we let the same state at time t depend only on whether or not it is a wet day at time t, that is time t and time t minus 1. Let us say only we are looking at just one time step ahead, that is this is t minus 1. Then the preceding model is not a single step Markov chain, because we are given that it depends on 2 days weather. However, for this problem it is possible to transform this model into a Markov chain, that is into a single step Markov chain. By Markov chain I mean a single step Markov chain, by saying that the state at any time is determined by weather conditions during both that day and the previous day. So, we are considering 2 days weather to determine the state. For example, I may say that state 1 is when both yesterday and today were rainy days. State 2 is yesterday was a rainy day, but today is not a rainy day. State 3 is yesterday was a non-rainy day, today is a rainy day, and so on. Like this we can define the states and then look at how the transitions take place. So, this is how we define articulately the states and then look at the transition probabilities using the conditions that were given earlier. So, let us see what we do here. state 1 we define if both today and yesterday are wet days, then I call it as state 1. And if today is a wet day, but yesterday is a dry day, I call it as state 2. If yesterday was a wet day, but today is a dry day, then I call it as state 3. Then if both today and yesterday are dry days, then I call it as state 4. So, how do I write here? State 1 in general I write t minus 1 and t minus 2, and t is some particular day that we are talking about. So, the previous 2 days t minus 1, t minus 2. So, we are in state 1 if both t minus 2 and t minus 1 are w w. By w I mean it is a wet condition. Then state 2 we are saying today is wet, but yesterday is a dry, which means t minus 1 is wet, t minus 2 is dry. Similarly, state 3 is t minus 1 is dry and t minus 2 is w. And then state 4 is both of them are d and d. So, you are looking at what is likely to happen in t given t minus 1 and t minus 2. So, states are defined based on the previous 2 days t minus 1 and t minus 2. Then how do we formulate the transition probability matrix now? So, what we were given remember is that if both the previous days have rained, the probability that it will rain today is 0.8, or both today and yesterday were rainy days, the probability that it will rain tomorrow is 0.8. Then if today is a wet day, but yesterday was a dry day, then it will be a wet day tomorrow with the probability of 0.5. So, this is what we have been given. With this now we should be able to formulate the transition probability matrix. Let us see how we do this. So, if the past 2 days have been wet days, I will demonstrate for state number 1. So, when we say we are in state number 1, what we are saying? We are interested in getting the probabilities for t. So, you are considering t minus 1 and t minus 2. So, when we are in state 1, both t minus 1 and t minus 2 have been wet days. So, we are in w w. Suppose you want to go to state 1 in t. What does that mean? State 1 in t means that t should be w and t minus 1 should be w, that is all. So, the 2 days must be w. So, what is the probability then? That you have to go from w w in the previous days to w in the next day. So, you have to look for the probability of the last 2 days being wet and going into wet days, and that probability is given as 0.8. If the last 2 days have been wet days, then it will be a wet day tomorrow with a probability of 0.8. So, this is what we are looking for. These two have been wet and you want to go into wet, this is state 1 transition. So, you want to go into wet and therefore, the probability is 0.8. You are in state 1, which means you are t minus 1 and t minus 2 are both w. What is the probability that you go to state 2 now? This is state 1, you go obtain 0.8. What is the probability that you go to state 2? What is state 2? State 2 is d and w. That is t minus 1 should be d and t should be w, but here t minus 1 is w and therefore, you cannot go to t minus 1 being d here and therefore, the probability is 0. You are in state 1, which is w w, you want to go to state 3, which means what? T minus 1 should be w and t should be d. This is possible and that will be simply from w w you have 0.8, therefore, w d should be 1 minus 0.8, which is 0.2. You are in state 1, which is w w, you want to go to state 3, state 4 I am sorry, which is d d. It is not possible because t minus 1 is d here and t minus 1 is w here and therefore, this is not possible, therefore, this is 0. So, the transition from state 1 to state 1, transition from state 1 to state 1, 2, 3, 4 are given as 0.8, 0, 0.20. These are the probabilities. So, this is how we formulate the transitions corresponding to each of the 4 states. So, state 1, state 2, state 3, state 4, state 1, state 2, state 3, state 4. So, at every time you have to look at 2 time periods. So, state 1 is defined by 2 time periods, state 2 is defined by 2 time periods. For example, state 2 to state 1 I want to go, then what we will do, this is t minus 1 is w, and we need, what do we need for state 2 to state 1? You were in state 2. So, you need another w here. So, dw and t minus 1 is w. So, you want another w here. So, dw to w, that is the transition that you need to look at. So, let us look at what is the transition dw to w, that is yesterday was a dry day, dw you want, that is yesterday was a wet day and day before was a dry day. So, the probability will be 0.5 here, like we have mentioned here, this will be 0.5. So, this is how you formulate the transition probabilities corresponding to each of the state. Assume take this particular state and look at what are the probabilities associated with going into state 1, state 2, state 3, state 4. And once you formulate the transition probabilities, then you can answer questions such as what will be day number 4, what is the probability that day number 4 will be in a dry state, starting with a particular condition. So, this is what we will do now. So, the formulation of the transition probability matrix for this particular problem is depending on the 2 time steps t minus 1 and t minus 2, and look at every time the 2 time steps and formulate the probabilities associated with 0.8. Remember, the state 1 is WW, therefore, because you are looking at time period t, this has to be WW, and similarly state 2 is DW. So, you must get DW here. Similarly, state 3 is WD and so on. So, starting with any particular state, you just move it and then look at whether you can get this kind of combination. If you can get the combination, there is an associated probability that is given, and that is the probability that you will get here. Now, let us say that Monday and Tuesday are wet days, both the days it has rained. Then we want to say, let us say we are planning for a cricket match or some such thing on Thursday, and Monday and Tuesday have been rainy days, and we want to examine what is the probability that Thursday is also a wet day. So, given that Monday and Tuesday are wet days, the probability of vector of Wednesday, you see what we need to do now, it is a Markov chain. Monday and Tuesday both have rained, which means you are in state number 1, because both the days have been wet days, you are in state number 1. You want to get the probability vector for Thursday, that means what is the probability that Thursday is a dry day or Thursday is a wet day. Instead of jumping directly to Thursday, which is also possible, but what we will do is first we will see what happens on Wednesday first. So, first we will get the Wednesday's probability vector. So, because Monday and Tuesday both are wet days, look at the transition probabilities. Monday and Tuesday are both wet days, which means that you are in state number 1. So, the probability vector for the next day will be simply this, because you are given to be in state number 1. So, I will write the probability vector as 0.80, 0.20. So, this is how you obtain the probability vector for Wednesday. Then probability vector for Thursday is probability vector for Wednesday into the transition probability, and so this you get as 0.80 etcetera. So, this is probability vector for Wednesday, this is the transition probability. So, you get the probability vector for Thursday as 0.64, 0.06, 0.16, 0.4. So, this is wet, this is wet, this is dry, this is dry. Therefore, the probability that on Thursday it will rain or on Thursday will be a wet day is probability of this going into wet and this being wet. This is state number 1, state number 2, both are resulting in wet condition, and this is 0.64 plus 0.06 is equal to 0.7. So, this is how you get the probability of a particular day being wet or dry, starting with this. So, in today's class we have summarized through a number of examples. I specifically considered 3 examples, the concepts of transition probabilities, the steady state probabilities, the probability vectors, and how we convert a two-step Markov chain into a single step Markov chain by appropriately defining the states. So, this concludes the discussion on Markov chain. Of course, there are large number of advanced topics related with Markov chain. For example, we may talk about hidden Markov chains and then large number of applications of Markov chain, which some of the applications I may be discussing towards the end of this course. But as far as theoretical coverage is concerned, this concludes the discussion on Markov chain. In the next lecture, we will start a new topic. Thank you for your attention.